The symbol that we'll use for angular velocity is a lowercase Greek letter omega. It looks like a W, but it's kind of a rounded W. You might have seen a capital omega. It looks something like this. But this is a lowercase. So in Greek we have capital letters, lowercase letters. This is a lowercase Greek letter omega. So that's what we'll use for angular velocity. And we can define angular velocity so that the average angular velocity is the change in theta over delta t. That gives us an average. If we want to define an instantaneous, we can take the limit of this as delta t goes to 0. So the instantaneous angular momentum will be the limit as delta t goes to 0 of delta theta over delta t. In other words, d theta dt. So if we have theta as some function of time, we can find the instantaneous angular velocity by differentiating theta with respect to t. Likewise, if omega is changing, so imagine we've got an object that is rotating but it's going faster, or it's going fast and slowing down, or anything in between, some crazy motion going one way or the other, back and forth, whatever, we can define the rate of change of the angular velocity. And what's that going to be called, do you think? That would be the angular acceleration. And the symbol that we use for angular acceleration is a lowercase Greek letter alpha. A capital alpha, actually, kind of being a little sloppy, looks like a capital letter A. Lowercase alpha, well, it looks like that. Like that, alpha. That's how it's usually written by hand. There's more of a if you have a script alpha or printed alpha in a textbook or something, it maybe has a little more structure to it. But when you're writing it on the board, that looks good enough. This is a lowercase Greek letter alpha. And so we can define the average angular acceleration as the rate of change of the angular velocity with respect to t. And then, if we want, we could define the instantaneous angular acceleration by the average angular acceleration in the limit that delta t goes to 0. And that would give us the instantaneous angular acceleration. And what is that? Well, that will be d omega dt. So if we have some time-dependent function of position, theta of t, we differentiate that once, and that gives us omega as a function of t, the angular velocity. We differentiate that, we get the angular acceleration as a function of t, etc., etc. Okay, well, does this look familiar? I would hope so, because this is exactly the way that we define very similar quantities. Angular position, linear position. Angular velocity is the derivative of the linear of the angular position. Linear velocity is the derivative of the linear position. Angular velocity is the derivative of the angular acceleration is the derivative of the angular velocity. Linear acceleration is the derivative of the linear velocity. Well, great. Well, when we had a specific situation of uniformly accelerated motion, we developed the 4 kinematic equations that worked with position, velocity, acceleration. Well, if these are defined exactly the same way, if we have a situation with a uniform angular acceleration, in other words, a constant angular acceleration, we should have exactly the same relationship between these quantities that we did with these quantities. Well, we're not even going to derive them. We're just going to write them down. Keeping, whenever we have an x, we're going to write a theta. Whenever we have a v, we'll write omega. Whenever we have a, we'll write alpha. You ought to be able to just write these down. That's what I'm going to do. The 4 rotational kinematic equations for uniform angular acceleration. Exactly analogous to the 4 kinematic equations for uniform accelerated motion. Exactly the same order, 1, 2, 3, and 4. Omega equals omega naught plus alpha t, which would be like v equals v naught plus at, x equals x naught, etc., etc. We've got theta equals theta naught plus 1/2 omega naught plus omega times t. theta equals theta naught plus omega naught t plus 1/2 alpha t squared, and omega squared equals omega naught squared plus 2 alpha times theta minus theta naught. We solve these exactly the same way as we solve the one-dimensional kinematic equations. Let's take a look at one problem. We'll just do one because we've seen how to solve this sort of problem so many times with the kinematic equations. We'll do one example and then move on. Let's say that we have a blender that rotates at 55.0 revolutions per second. It then accelerates at 1,650 radians per second squared as it rotates through 40 radians. So what's happening? The blade of the blender is speeding up at this rate as it rotates through 40 radians. The question is, what is its final angular velocity? Okay, well, let's write down the variables, but even before we do that, let's notice here. The blender rotates at 55.0 revolutions per second. What is that? What is that? What is that quantity? Well, it sounds like an initial angular velocity, but it's not in radians per second. So one thing we have to do is convert that to radians per second. 55.0 revolutions per second means it rotates through 55 complete revolutions every second. We need to convert that to the units that angular velocity has, which would be radians per second. So we need to convert the revolutions to radians. So what's the conversion? Well, one revolution is 2 pi radians. So we're going to multiply by 2 pi radians per revolution, and that will give us the angular velocity in terms of radians per second, and that is 346 radians per second. Now let's write down our variables. Exactly like we had it before. What are the variables? All right, we'll have theta naught theta, initial position, final position, omega naught omega, initial angular velocity, final angular velocity, alpha, angular acceleration, and t. There we go. Okay, 6 variables just like we would have had with one-dimensional kinematics. So what are our values? Well, theta naught and theta. We can define our initial angle any way we want, the initial orientation of the blender, so we'll set that equal to 0. Our final theta, well, we know that it rotates through 40 radians, so our final angle is 40 radians. Omega naught, the initial angular velocity, well, that will be what we converted here, 346 radians per second. Final angular velocity, well, that's what we're looking for, so that's what we want. Angular acceleration, well, that looks like this, what this is. So radians per second squared, what would the units of angular acceleration be? Well, that would be radians per second squared, so that must be alpha. So 1650 radians per second squared. And time, we do not know the time. What are we looking for? Omega. What equation could we use that has an omega in it and in which we know everything else? Well, which equation do you think? Well, the fourth one. Turns out the fourth one. So, what do we have? We've got omega squared equals omega naught squared, which will be 346 radians per second squared, plus 2 times alpha, 1650 radians per second squared, times theta minus theta naught, 40 minus 0, 40 radians. Okay, multiply that all out, and what do we get? We get 2.52 times 10 to the 5th radians squared per second squared, radians squared per second squared. Okay, good. Radians squared per second squared. Take the square root, and omega equals 502 radians per second. Okay. Very good. Just like our old one-dimensional kinematics problems. They're just stated in a little bit different way, where we've got, rather than position, velocity, acceleration, we've got angular position, angular velocity, angular acceleration. But solving the problems is very, very similar. Let's see if we can relate some of these angular quantities to some of the linear quantities. Can we relate some of these things to positions and distances and velocities and linear accelerations? Well, yes, we can. Let's do that. Let's go back to our view of just a particle going around in uniform or a circular motion, but not necessarily uniform circular motion. The velocity could change in this case. If the object goes around an entire circle, we know that the distance traveled is the circumference, which is the radius of the circle times 2 pi, where 2 pi is the angle through which it rotated. One circle, one complete revolution is 2 pi radians. Well, the fact is that if it travels a shorter angle or smaller angle, let's say d theta, then the distance traveled, we'll call that ds, is equal to r times the smaller angle, d theta. So that angle could be 2 pi, in which case the distance is the circumference, and r is the distance is r times 2 pi. If it's a smaller angle, d theta, the smaller distance is ds equals r d theta. Let's divide both sides by t. Not t, dt. And what do we get? What is ds dt? ds dt is the distance traveled divided by time. Well, that's just the linear velocity. And in particular, I'm going to call this the tangential velocity. It is the velocity of the object as it's moving around the circle, tangentially to the circle. So we'll call that v sub t. Equals r times, what is d theta dt? Well, that's the angular velocity, r omega. So that is r omega. So this gives us a very simple relationship between the tangential velocity and the angular velocity. If we differentiate both sides of this, what do we get? We get d v t dt, differentiating with respect to t, equals, assuming r remains constant, so r is not changing as it's going around the circle, r d omega dt. Then what do we get? Well, dv dt, that's the acceleration. And in this case, it's the acceleration along the direction of the circle, and again, tangentially. So this would be a sub t equals, and what is d omega dt? That's the angular acceleration. So r times alpha. Okay, there we go. So that gives us a very simple relationship between the angular acceleration and the tangential acceleration. But we also know that there is a centripetal acceleration, which was equal to v squared over r. And what v was this? Well, that is what we were calling the tangential velocity, v sub t squared. We can write this as v sub t squared over r squared times r. So I'll add another r down here and then an r in the numerator. But vt over r, what's vt over r? Well, that would be omega. So the centripetal acceleration is r omega squared. R, and then vt over r is omega, squared is omega squared. So we have a very simple relationship that relates the angular properties, r omega, to the centripetal acceleration, a sub c. Okay, very, very good. Let's now take some of these kinematic ideas and move into dynamics. Can we start to understand what is it that would cause an object to have the rotational motion that it does? Just like when we were looking at linear motion and we developed the dynamics to understand what causes an object to have the motion it does, what causes a motion to have the rotational motion that it does?